chapter 6ing, and we started talking about nomenclature. We got through a lot of nomenclature last time. We talked about type 1 ionic compounds. Remember, type 1 ionic compounds, or an ionic compound just in general, is always a metal and a non-metal together. And remember that when we do have that situation that occurs, because of their periodic trends, what occurs is we will always have a transfer of electrons from the metal to the non-metal. That again is what basically causes the ions to form, and what keeps together an ionic compound is the attraction between those ions, where the metal becomes a cation, non-metal becomes an anion. And again, a reminder, as we'll talk more about when we get into bonding here in a second, that there's absolutely no sharing of electrons here in this situation. It is the attraction between the positive and negative that holds that together. Whenever we have a metal involved, and that happens always with ionic compounds for sure, it is always really the most important thing. And what makes this a type 1 metal is it has a fixed positive charge. And that on the periodic table is group 1, 2, 3. And from the transition metal region, zinc, cadmium, are silver. So as we talked about last time, as soon as you kind of see any of those ones there in terms of the metal, you basically you don't have to figure out pretty much anything else. You could just roll right into the name. And in this situation, we just use the whole name there of the metal, or the cation. And the non-metal, as we talked about, gets the sort of IDE treatment at the end of the name. We get rid of part of the last part of the name, or even maybe a little bit more than the last part of the name, and it ends with IDE. Remember, as well as we talked about, metal involved here, so we never use prefixes, right? So even if there are multiples of either of those, the metal or the non-metal, no prefixes are used. So again, if we had something like CaCl2, calcium metal, chlorine non-metal, calcium group number 2 on the periodic table, whole name there of the calcium, and other one becomes chloride. Again, the 2 here has no bearing on the name. The 2 is there for another important thing that we talked about, which is whenever you put together an ionic compound's formula using the positive ion, thank you, and the negative ion, it does need to equal 0 overall charge. So again, that is why we have the 2 there. That's because calcium is group number 2 that has a +2 charge. Chlorine is group number 7 that has a -1 charge. And when we put it together to get us to 0, we would need an extra chloride there. And that's going to give us an overall -2 that balances the +2. And that, again, is how we get to the formula: 1 calcium and 1 and 2 of the chlorides. We also talked about type 2 ionic compounds. Also, same as above, it is still a metal and a non-metal, and still have the transfer of electrons just like above. The only difference here is, again, the metal, and that metal is going to be a transition metal, or as we talked about, just to the right of it, below the staircase. What those guys have in common is they have a variable positive charge, and that means that you do have to do just an extra little bit of work here to figure out what is the charge on the metal. You could do that pretty easily because you will always know the charge of whatever it is bound to. So as we talked about there, FeCl2. Once again, metal, non-metal tells me it's ionic. The metal here is dead center there in the transition metal region, which tells me it's a type 2 compound. And I need to figure out the charge. So once again, we have 1 iron. We have Cl, which is group 7, has a -1 charge, and there's 2 of them. That gives us a -2 overall charge. That means to balance it out to 0, our iron, again, in this case, will have to have a +2 charge to do so. The only difference in how we name it is we do add a Roman numeral to indicate the charge. So this would be iron Roman numeral 2. Once again, the Roman numeral is not how many metals you have, but it is the individual positive charge if you took one of those metal ions out. And same deal here, still no prefix happening. So this would just be iron 2 chloride. So as we talked about last time, good way to remember not to use a prefix in the wrong situation is you should probably never use a prefix with a metal. So again, if you see a metal there, you should probably not be laying up some prefixes in your names because it's probably going to be incorrect. The last type of naming we talked about last time was a type 3, and this is a little bit different. This is sometimes referred to as a molecular compound, and it has covalent bonds, so sometimes maybe people call it covalent as well. And the difference also is what's involved. So you always know you're dealing with an ionic bond situation if you have a metal and a nonmetal together, but in a type 3, it's actually two nonmetals together. And as we'll talk more about a little bit later, the main difference here is we actually will get sharing of electrons. So in an ionic compound, we don't have sharing of electrons, but here we do. And this is actually, as we talked about at the very end there, where we do use prefixes. So this is the appropriate place to use prefixes in the naming. And as we talked about, there's a few prefixes there. We have our mono for 1, our di for 2, our tri for 3, tetra for 4, penta for 5, hexa, hepta, octa, nona, and deca, all the way up to 10. Now, there's a couple of rules that we talked about with these prefixes, which is one of them really involves mono. We do not use on the first name. But again, it's okay on the second. The other sort of thing that occurs is we end up sometimes with vowels that back up to each other from the prefix last letter and also the first letter of the element. So if you have kind of two O's that end up back to back or an A and an O, typically we take out the vowel that comes from the prefix when we're doing this. Two I's are okay. So again, as we saw this one last time, I sort of covered all the rules. We have carbon, which is a nonmetal. We had oxygen, which is a nonmetal. So once again, this is going to be a type 3. We have only one carbon, and the prefix there for one is mono. Again, here we would not use it on the first name. So how we usually name the first element is just to use the whole name of it with the appropriate prefix. In this case, we don't use the prefix, so this would be carbon. On the second guy there, he ends up with the IDE at the end of his name, kind of like everything else, and with the appropriate prefix, which again we can use here. And once again, with the mono and the oxide, as we talked about, that's going to kind of back us up to two O's. We would get rid of one of the O's. And again, this would be carbon monoxide as the proper name. So the way that we name type 3 is prefix if needed, and the whole name of the first element, then prefix for the second element, and the second element gets the normal kind of non-metal IDE ending, and that is sort of how we go through those guys. Any questions on any of that naming stuff that we talked about last time? No. What's that? Yeah, probably. Yeah, yeah. So you will be able, if you're asking, do you have to write the name, and do you have to write the formula? Yes. So if you're given a name, you'd probably have to write the formula like we did in some of those examples, or if you're given a formula, you would have to provide the correct name. Yeah. So kind of like what we did in those examples last time. Yeah. Other questions? Yeah. Yeah, I think you should know the prefixes. I would say definitely up to 8. Yeah, it should be fine. Yeah. Other questions? Okay. All right. The last type of naming that we're going to talk about is polyatomic ions. And polyatomic ions are kind of weird things. They are basically groups of nonmetals that are actually bonded together through sharing of electrons, but they actually end up with an overall charge, so they're considered ions. So nonmetals and nonmetals usually will share electrons, but because of who they're sharing electrons with, they actually do end up with an overall charge altogether. So for example, if we take a look at this one right here, NH4NO3, if we take a look at it here, NH4NO3, this guy actually contains two polyatomic ions. If you split it up right about there, you actually have two different ones involved. And if we look at it, this guy is NH4 plus. So that one nitrogen and those four hydrogens, they are actually sharing electrons. They stay together completely. They move around together. The whole thing moves as one unit. They will never break apart into like nitrogen and hydrogen by themselves. They're just kind of locked in through sharing of electrons, and they move around. And that entire thing has a +1 charge. So altogether, that kind of unit of NH4 has a +1 charge. If we look over here, this is another polyatomic ion, which is NO3 minus. Same idea here. This nitrogen and three oxygens are sharing electrons. They're locked into each other. They move around as a whole unit. It doesn't break apart ever into individual nitrogens and oxygens or anything like that. And overall, it has a -1 charge altogether. So ultimately, these are still ions. This is really like your cation. This is really like your anion. So even though there's a bunch of things together in this sort of unit, they are still ions, and we treat them the same way in a sense as we do type 1 and type 2, which means when we put the positive guy together with the negative guy, we still need to equal 0. So the overall charge for the formula needs to equal 0, just like we do with a normal ionic compound. And when we do that, in this particular case, we're taking something with a +1 and something with a -1, which means actually we just need one of each of those. So when we put that together, that is how we get to the formula that's above. We take the NH4, which is +1, and it's okay to hang out there with the NO3, which is -1, and there shouldn't be a negative there. I got a little over negative there. And overall, the +1 and the -1 equals 0. So this is really just a ionic compound that kind of each ion is made up of a kind of a unit of nonmetals that are hanging out together. Now, in terms of polyatomic ions, they have special names. This particular one is known as the ammonium ion. Not to be confused with, I think, something we saw earlier, which is NH3, which is ammonia. NH3, no charge, ammonia. NH4 plus ammonium. NO3 minus is what is known as the nitrate ion. Now, one of the good things, I guess, of polyatomic ions is when we name polyatomic ions, we simply just use the whole name of the polyatomic ion. So whatever the name of that polyatomic ion, we use it in the naming. It also does not matter how many of those you have. So if I have like 30 NH4s, it doesn't matter. It's still just going to be ammonium. If I have 2 of the NO3s, it's still just going to be nitrate. So having more than one polyatomic ion in a formula, and you have to name it, will have no effect on the overall name. So in this case, we simply will just put both of those names together, and this compound here is known as ammonium nitrate. So that is ammonium nitrate. Now, I will say we're going to see a table from your book and of some polyatomic ions. And pretty much NH4 plus is probably the only positive ion that you will see in terms of a polyatomic ion. There are others, but you probably won't see them. So that's probably the only positive one that you see. So what happens in most cases with polyatomic ions is they hook up with metals. So metals which are positively charged tend to go find some polyatomic ions. So a lot of times when you're dealing with polyatomic ions, you most likely will have a combination of a metal and a polyatomic ion. And as we talked about with our earlier naming, whenever a metal's involved, it's still the most important thing. So ultimately, because a metal's hooked up with a polyatomic ion, you still have to really follow the type 1 and type 2 rules, which is, do I need a Roman numeral or do I not, based on the metal? So it kind of falls that way. So for example, if I took NaNO3, this compound, again, we could break apart right here, and I see a metal, which is sodium, which is Na plus. That is my polyatomic ion that we just saw there, NO3 minus. And once again, the reason the formula is like this is this entire thing is a -1 charge. This entire thing is a +1 charge. And again, you just need one of each to put them together to get the NaNO3. It equals 0. And because there's the metal, that is the most important thing. So when we see something like sodium, it is a type 1 metal, which means we do not need a Roman numeral, right? So we just do the same thing that we did previously, which is we just use the whole name of the metal. We don't need a Roman numeral because it's sodium. And we still use just the whole name of the polyatomic ion. So this would be known as sodium nitrate, right? Just kind of putting it together, following really type 1 type rules. Now, also, you could have a metal that's a type 2 metal that could hook up with a polyatomic ion. So instead of sodium, let's say we threw in there a little bit of iron. And we'll do that. And let's say we have FeNO3 in parentheses 3. Once again, we would break this up right here. We would look at this. This is a metal. This is our polyatomic ion. And again, the metal is always the most important thing. So when we see the metal, we see, again, iron's in the transition metal region, which means it's a type 2. That should trigger that you need a Roman numeral. And you also, again, need to figure out the charge on the iron. So in this case, we have 1 iron. NO3 is NO3 minus. And there's not just one of them, right? There are 3 of them. Parentheses, we got 3 of whatever's in the parentheses. So again, here we would have kind of 3 of these guys, which if we added up the negative charge, -1, -2, and -3. So that tells us in this case our iron would have to be what to equal 0? +3. And again, because it's a type 2, that's all we need for the type 2. We will go with iron Roman numeral 3 because of the charge. And once again, as I mentioned earlier, it doesn't matter how many of the polyatomic ions you have. We still don't use prefixes with these. Again, because of metals involved, right? So we don't want to use any type of prefixes. We just use the name of it. So this would still be nitrate in this case, yeah. Question on that there. So I will say that's probably most often how you're going to kind of see polyatomic ions. They're definitely going to be kind of hooked up probably with a metal. As again, NH4 plus is kind of the only positive one that's kind of hanging around. Any questions on that? The other important thing with polyatomic ions is what you see with what I wrote in that formula. Why did I not write the formula like so? That would imply I have how many oxygens? 33, which is a little bit much when I really only have 3, 6, and 9, right? So whenever you have more than one polyatomic ion, you always have to put parentheses around the polyatomic ion, and bottom right, you need to put how many of those ions that you have. So you will use parentheses a lot, sometimes with polyatomic ions. And again, it's just indicating how many of those ions you have available to you. Any questions on that there? Yeah. The answer is probably not the answer everybody wants to hear. It's on the table, and you just have to kind of know the formula and the charge and the name that goes with it. So we're going to look at this table right now. We're going to talk about ways that will be easier to sort of figure these things out without having to maybe memorize every one individual or anything like that. So there are some patterns that occur with polyatomic ions, which can make them a little bit easier to sort of figure out. So this is a table of polyatomic ions. I think it's like from your book, if I'm not mistaken. One of those is. I think that previous one was there. And this is some of the polyatomic ions. And as was the question asked, you do have to kind of know the name and the charge to be able to kind of put everything together correctly. So when we look at a table like this, there are polyatomic ions that are related to each other. So for example, we just saw NO3 minus, which once again is 1 nitrogen, 3 oxygens with a -1 charge. That's known as nitrate. The one that's related to it is NO2 minus, 1 nitrogen, 2 oxygens, also has a -1 charge. This is known as nitrite, ITE. For example, if you look at sulfur over there, there's SO4 2 minus. That is 1 sulfur with 4 oxygens and a -2 charge. That is known as sulfate. SO3 2 minus. Again, 1 sulfur, 3 oxygens, has a -2 charge, is known as sulfite. So let's take a look at just these two, the groupings of two that are related to each other. Again, to look at sort of the pattern of how it might be helpful to think about these things. Again, when we look on the nitrate and nitrite, the absolute only difference between these two is the number of oxygens. They both have 1 nitrogen. They overall both have a -1 charge. In one case, one has 3 oxygens, and in the other case, it has 2 oxygens. It's the only difference. Now, the one with the most oxygens, right, is the NO3 minus, right? It's got 3 oxygens versus the other one that has 2. And that one ends in 8. The one with the least number of oxygens typically end in "ite." Good way to remember that is like you ate too much. Yes, the one that has 2 more oxygens is the one that will end in 8. Over here, this is these two. The only difference between them, again, is the number of oxygens. We have 1 sulfur, and they're both -2. One has 4 oxygens, one has 3 oxygens. So again, the only difference between them is just that 1 oxygen. The one with the most oxygens, which is the top one, ends in 8. So that is sulfate. The one with the least number of oxygens ends in "ite." So a really good way to sort of get a handle on these is to kind of group them together and understand, for example, how to manipulate one of them. And what I mean by that is you could choose, for example, to maybe remember all the 8s. And then if you need "ite," you just take off 1 oxygen and you're there, and that's it. So like I know nitrate's NO3 minus, but I need nitrite. It's NO3 minus, so it should take 1 oxygen off, NO2 minus. Or I know sulfate, it's SO4 2 minus, but I need sulfite, that's 1 oxygen less, SO3 2 minus. So those are good ways to sort of put these guys together, to sort of group them together, and just remember maybe one of them and know how to adjust it up or down depending on how many oxygens you might need, or is it an 8 or an "ite." Now, there's also ones that are groups of 4 that are related to each other, and that is right here with the chlorine ones. And if we look at the chlorine ones, I'll just do it right here. There is ClO4 minus, there is ClO3 minus, ClO2 minus, and ClO minus. Once again, all these guys stay together as groups, and every single one of these guys have a -1 charge. And the only difference between all of them is how many oxygens that they have. So in a group of four, we could still do our same sort of pattern, which is typically speaking, the one with 8 has the most oxygen, and the one that ends in "ite" has the least oxygen. So if we were going to break this group of four that are related to each other, I would break it right here. Everybody to the right has the least number of oxygens, and everybody to the left there has the most oxygens. And we know if we, for example, start on the right-hand side, if it has the least number of oxygens, it should end in ITE. So this would be chlorite. And you know what? I don't have to think too much about the next guy because I know pretty much his ending is also going to be chlorite. You clearly cannot have the same name for two different things. So what happens when you have a group of four, the one with the least number of oxygens in that group ends in ITE, but begins in hypo. Hypo means less than, yes? So it is the least number of oxygens. So that is chlorite and hypochlorite. Again, the only difference between that is the number of oxygens. Now, if we take a look at the two on the left, which has the most oxygens in that group of four, they should end in 8, right? Like 8 too much. They should all end in 8. And they have chlorine in there. So this guy is named chlor 8. This guy will also be chlorate because it has the most oxygen. Just like on the other side, we cannot have the same name for two different things. So when you have a group of four, the one with the most oxygen will end in 8, but also start with per. So that is perchlorate, chlorate, chlorite, and hypochlorite. And that group of four is probably the most common group of four that you'll come across. But just to show you how the names relate to each other, where do we find chlorine on the periodic table? Group number 7. Also in group number 7 on the periodic table is bromine, right? So if I took chlorine out of this guy here and put bromine in, BrO3 minus, what do you think the name would be? It definitely wouldn't be chlorate because it no longer has chlorine, it has bromine. So this would be bromate. Yeah. See how that works, bro? No, I'm sorry. People say bro now, right? If I took chlorine out of that guy and put it in, put bromine in this one, so the chloride, it would be bromite. So the best way as I'm talking here to sort of figure out these names or kind of learn these names is to learn how to kind of manipulate them by going up an oxygen, dropping an oxygen. And again, that requires you only to kind of know a baseline of, like I said, maybe the 8s on the table or maybe the ites on the table. And if you know how to adjust them, you could get there, right? Now, if this was PO4 3 minus, and again, that's 1 phosphorus and 4 oxygen with a -3 charge. This is known as phosphate. What would you imagine PO3 3 minus would be called? So this is 8, which means it has the most oxygen. 1 down from 8 would be phosphite. Yes, just like so. Yeah. So that would be phosphite. Yeah. So this is probably the best way to kind of approach this is again to know how to manipulate it, right? Let's say I had, for the fun of it, let's say we had PO5 3 minus. What would the name of that one be? Well, we already have phosphate, so if it has to go up from just the 8, what happens to the front of it? Yeah, so that's perphosphate, yeah? Or if you drop oxygen off of this one. Yeah, so again, just kind of moving around and manipulating is a good way to kind of do that. Like I said, and that only involves an investment of I'm just going to take the 8s and know how to kind of move up and down. along the way, and you'll be good on most of those guys that are on the lists along the way. Any questions on how to do that there? That's, again, probably the best way to sort of approach it. Now, there are a couple other things that you'll see on this list in terms of names. Um, but again, you just want to think about it logically. Let me just go back to where we were there. Now, if we take something like, for example, we take something that's on that table, which is CO3 2 minus. That's one carbon, three oxygens. That's carbonate ion. So if I had CO2 2 minus, that should be the guy on the left's carbonate. That guy should be carbonite, right? Carbonite. Yeah. I know it's not hypo, right? Because if I drop one more off, then perhaps I'm getting to hypo, right? But here I am just moving from 8 to ite, right? So if you're starting at 8 and you add an oxygen, then you're going to add the per to the front, right? If you're starting at ite and you drop an oxygen, you're going to add the hypo to the front. So again, you want to think of it in that sort of pattern of 4 and then how to manipulate. Now, something else that you'll see on that list is they'll take this guy and they actually will put a hydrogen in front of it, which is actually an H plus, and that will give you HCO3 minus, and you add the hydrogen here, and the charge does change. It goes from -2, and a positive charge leaves you a -1 left over. That's why it still has a negative charge. Now, this is not super hard to figure out the name here. We know probably it's CO3 at the end of it, so I would say that's probably in the name, right? And what did I put on the front of it? Yeah, so put those together and you get hydrogen carbonate, yeah, would be the name of this. This is also known as bicarbonate, yeah. Helps with the indigestion you're having right about now, but perhaps that's along the way. That's bicarbonate. Bicarbonate is an old school name that they use instead of hydrogen. You also sometimes, we saw this guy earlier, SO4 2 minus. If I put an H in front of this guy and end up with SO4 minus, this was sulfate, if you remember. What should this be? What did I just put in front of it? Yeah, I put a hydrogen, and that is sulfate. Yeah. That also is sometimes referred to as bisulfate as well. So that bi is sometimes used still today a lot. Bicarbonate, bisulfate is the same thing as hydrogen carbonate and hydrogen sulfate. We're getting an idea of how to kind of manipulate just these things. Yeah. Yeah. So let's take a look at this and we'll try to get rid of all my scribble on the page, perhaps. Yeah. All right. So why don't you try naming some and see what you come up with? Let's go with yeah, let's go with Li. Anyway, ClO2. Let's do um Na2SO3. Let's do FeSO4. Let's do all right, so why don't you give the name for those, and then let's go with why don't you write the formula for something. Let's go with calcium hydroxide. And let's do cobalt to nitrate. All right. So names for the top ones and formulas for the bottom. Should hopefully be able to find those polyatomic ions on this chart. I hope, yes. Okay, let's take a look, see how you're doing. So once again, we're going to look at this, and we got LiClO2. Even though there's a lot of letters in there, we still want to kind of approach it like we've done everything else, which is we really kind of want to identify what we're dealing with. So we should hopefully know lithium is a metal, and definitely if we see something like this, which is a bunch of letters together, that's probably a polyatomic ion, right? So we got a polyatomic ion, we got a metal. We know always from our naming conversation, metal's really where we should start with, right? And Li is group number one on the periodic table, which means it's a type 1 metal, which means that's good because we don't have to figure out anything about charges or anything like that. We don't need Roman numerals to do this. The next thing we probably want to again identify here is the name of our polyatomic ion because we're just going to use the whole name completely. We find it here, right? And that's one of those four that we talked about. It has the least number of oxygens, but not all the way to the least. And that is chlorite. And that is lithium. And that's all we have to do is just put those two together here. And that would be lithium chloride, right? Again, because the metal is type 1, we don't need any Roman numerals or anything like that along the way. Once again, we do not typically use prefixes with polyatomic ions. The absolutely only time you would use a prefix is if the polyatomic ion itself actually had a prefix in it. And that would be something like this down here. You can see that one has that actual prefix, but that's part of the polyatomic ion's name. It's not like us putting a prefix on it. So that would be the only time you'll ever see a metal and a prefix together is if a polyatomic ion has an actual prefix in its name. All right, coming over here, same idea. Sodium is a metal. That looks like a polyatomic ion because there's a bunch of it there. So once again here, metal taking the precedent and the priority. Sodium, much like lithium, also group 1, which means it has a fixed positive charge. It's a type 1. We can pretty much write sodium down because that's how we name it, right? Whole name, no Roman numerals needed. Now we just need to identify what SO3 is. Perhaps I memorize SO4 2 minus, which is sulfate, but this is one oxygen less. So that then would be sulfite, right? So again, understanding how to adjust those if you happen to memorize sulfate. Maybe you chose to memorize sulfite and you got it, and then you add an oxygen to get sulfate. So whichever way you want to go. Any questions on those two there? Coming down here, we see metal. We see SO4, which again is a polyatomic ion. Multiple things together there. Once again here, iron in this case is a transition metal, which means it is a type 2 and can have multiple charges. So we go through our normal type 2 situation, which is I'm not sure what the charge is. I once again will know the charge of this guy. That is our sulfate, which is SO4 2 minus. So since this is 2 minus, the iron here must be plus 2. I know I only have one of those polyatomic ions because I do not see any parentheses, right? So there's no parentheses around it or anything like that, or a number on the bottom. So we just have one. By the way, when you have only one polyatomic ion, you don't need parentheses around it. It's just when you have more than one that you have to put the parentheses. So that would then mean that this would be iron, Roman numeral 2, once again, like we've been doing for the charge. Whole name always for our polyatomic ion, which is sulfate. Any questions on that one? Yeah. It's 2 for the Roman numeral because the Roman numeral indicates the charge on the metal. And in this case, the iron has a plus 2 charge. So that's where the 2 comes from. Yeah. And that's also for earlier on as well when we did type 2 before. Whenever you have the Roman numeral, it's not how many metals you have or anything like that. It's just if you took one of those by themselves, what the positive charge would be on it. Uh-huh. But the charge on SO4 is 2 minus. So this SO4 2 minus, this is the actual unit. So if you drew it, which you will know how to draw shortly, it is this when you draw it. And that's what the 4 represents. It represents that there are 4 oxygens attached to the sulfur. This entire thing has a -2 charge overall. So that entire kind of unit has the -2 charge. And that is what the Roman numeral indicates is what the charge is. Not what the charge is, but it would be what the charge is on the iron. And that is why the iron has a +2 charge because the negative guy has a -2 charge. So that equals 0 when you put it together. Yeah. How do I know that sulfate's negative charge? Again, just back to the list and remembering it. One of them's the formula for it. Yeah. It should be right here. I kind of wrote over it, but it's right there on the. It's right there, yeah, on their chart. So remember the charge, right, is the thing on the top, right, and use that to back calculate the left there. Where it says, I'm sorry, where? Yeah, yeah. Hang on, let me erase what I have up here. Right here. Yeah. No, HSO4 is hydrogen sulfate because it has a hydrogen in front of it. Yeah. So that would have been the name if the formula was like Fe parentheses HSO4. It would have been that one. Yeah. Other questions? Yeah. Yeah, it didn't get a Roman numeral. It didn't get a Roman numeral because again, the metal is always the most important thing. And that metal is what we call the type 1 metal that we were doing the other day. And it's in group number 1. And basically, what that means is, as we talked about, it has a fixed positive charge. So, no matter what sodium hooks up with, it will never be anything other than a +1 charge when it makes it. So it has that fixed charge. And that's why we don't need the Roman numeral because there is no situation where something like sodium would have like a +2 charge or a +3 charge. It is locked in and fixed as a +1 charge. So the idea of naming is just to tell people what you're dealing with, right? So because it's sodium, everybody knows it has a fixed charge. You don't need to tell people, hey, it's sodium 1. It can only be sodium 1. The reason we need, for example, a Roman numeral with iron is it's a type 2 metal. And in certain situations, like we have here, the iron that we're dealing with is the one that has a +2 charge. But you could also have an iron that has a +3 charge. So when we give the name, we're telling people, hey, in this situation, we're talking about the iron that has a +2 charge. Otherwise, if this was the iron with a +3 charge, the formula would be a little bit different. But if it was one with +3 charge, we would say it's iron 3, and that tells the person, oh, that's an iron with a +3 charge. So, and that happens because those guys have the ability to make variable type charges or multiple different positive charges. And again, that's just like we talked about last time. That's basically your transition metal. And just to the right underneath it, where things like lead and tin are located, they have the ability to make different types of positive charges. The only 3 exceptions to that is the zinc and cadmium and silver, which are classified as type 1 metals because zinc and cadmium have only the ability to do +2 and silver is locked into +1. So even though they're technically transition metals, they also have that kind of fixed locked in charge. And that's why we don't use Roman numerals with them as well. Yeah. Other questions? Yep. All right. Over to the right here, we kind of look here. We see copper, which is a metal. We see a lot of stuff there, which definitely is a polyatomic ion in our situation. So once again, we look at the periodic table and we see coppers in the transition metal region. So that tells us, as our conversation we just had a second ago, it is a type 2 metal. It can have multiple charges. We need to first figure out the charge, and we also need a Roman numeral. So copper is going to be some type of charge. When we know this guy on the list, this one is carbonate, but it has a hydrogen in front of it. So this is our hydrogen carbonate right about here, or our bicarbonate, whichever one you want to use in terms of the name. And that is HCO3 minus. So that entire thing has a -1 charge. The difference, though, is what do I see around my polyatomic ion in this formula? Yeah, and that also a number on the bottom, which means I don't just have one of those, I have how many? Two. So I got a double shot of this, right? That means if I'm counting up my negative charge, it's a grand total of -2, right? One from each. That's very important for my copper because in order to get to zero, it needs to be +2 to balance it out. And now I got everything I need for this name, right? That's going to be, go right underneath here, maybe. Copper Roman numeral 2. Once again, the 2 is for the charge. And again, it doesn't matter how many of those polyatomic ions there are. We're just going to use the name. And you do have a choice in this case. You could use bicarbonate if you want, or you could use hydrogen carbonate. It's your choice, whichever way you want to go. I'll go with hydrogen carbonate underneath since I'm running out of room. Hydrogen carbonate. But it could also be called copper 2 bicarbonate if you want to use that name as well. And again, that's because that hydrogen carbonate or hydrogen sulfate can be bisulfate or bicarbonate. They're very commonly still used. Any questions on those names there? Yeah. Yeah. For type 2. Type 2, you always have to use a Roman numeral, even if it's 1. So if you had a copper 1, copper with a +1 charge, you would need to say copper Roman numeral 1 because copper also has the ability to do +2. So that way you could tell. The exception to transition metals in Roman numerals is those three. You don't need them, the zinc, cadmium, and silver. Other questions? All right, we're going to do some formulas here. We're going to just kind of build it. So I see calcium hydroxide. By the way, you might also notice on this list, there are a couple polyatomic ions that actually do end in IDE. Hydroxide is a very common one. Cyanide is another one. So there are a few polyatomic ions that don't end in 8 or I. They actually end in IDE. And I would say hydroxide, cyanide is kind of the two common ones. And we're still just going to take our basic units. These are ionic compounds because there's a metal involved. And I got calcium, and I know calcium is group number 2 on the periodic table, which means it should have a +2 charge, right? And hydroxide I could find right here at the top of the table. And hydroxide is OH minus. Again, that O and the H all stays together, and it has a -1 charge. So I have a positive thing and a negative thing. When I put it together, it needs to equal what charge? 0. I need more positive or more negative here? More negative. So I don't need 1 hydroxide. I actually need 2. That's going to give me a -2 to balance out my +2. So that's going to give me a formula of Ca. I have how many of those polyatomic ions? I have 2, which is more than 1, which means when I write my formula, I need a parentheses of OH, and on the bottom right, how many I have, right? Which is 2, yeah. So we end up with CaOH2 in this case. Again, the 2 indicating that we have 2 hydroxide ions, each have -1, gives us a -2 overall charge, and obviously the calcium with a +2 charge. Question on that one there. All right, last one here. If we could find in my scribble, let me erase something. We'll go above it. There, we'll go above. All right, we'll go with this one here. We have cobalt, Roman numeral 2, nitrate. Good news is when I see cobalt with a Roman numeral 2, what type of charge does the cobalt have? What is the Roman numeral? 2. So what type of charge does cobalt have? +2. Yeah, so again, that's what the Roman numeral indicates. So I know the cobalt here has a +2 charge because frankly, it told me it has a +2 charge, right? So that's good. I didn't have to worry about this because again, that has a fixed charge and I know it's in group 2 and that's how I figure out the charge for those guys, right? And if you have a name that has a Roman numeral, it tells you what the charge is on the metal. Nitrate, we saw a few times already, right? That is NO3 minus. That means once again, when I put this together, I'm going to need a little extra nitrate here, right? I'm going to need not 1, but 2 to balance it out. So now I could just put my formula together, a CO. I got 2 nitrates, which means 2 polyatomic ions. put it in a parentheses and then the number on the bottom, right? That's what I got there. Question on that there. You'll be responsible for the polyatomic ion table that's in your book, yeah. And on the review sheet, it'll say which ones you should probably know for sure. But make sure you're familiar with the tables in your book. I also provided in the handout a couple other polyatomic ion tables from some other books. And I think even on Canvas, there's like a chart of them, just in case you come across some, maybe on homework or something like that, that's maybe not on your table. Your table is not a very big, extensive list of them. So if you can't find them, there should be a table, I think, on Canvas, and there's a couple other tables in this handout just in case you want to reference it for some that maybe you might come across as you're doing it. Any questions on that? That is naming, and I think we should take a break and think about what we just did. So now that we're done with naming, we'll talk about the other half of the chapter, which is bonding. So we're going to talk about bonding here, the different types of bonding. We're going to talk about how to draw Lewis structures and all that good stuff. Chemical bonding and bonding in general basically do relate to, obviously, the nomenclature we just talked about. And there's kind of like two types of compounds that we named. There's ionic compounds, which always contains a metal and a nonmetal. And there's really covalent compounds or molecular compounds that contain two nonmetals. And pretty much bonding is a breakup of those things. And we're going to talk about how it all comes together. So let's start with Lewis dot symbols. Lewis dot symbols, nowadays they just generically call them a lot of times just electron dot symbols. And they basically represent the element and the valence electrons that are involved in bonding. And when we look at electrons, there's only certain types of electrons that are involved in bonding, and those are valence electrons. For example, if you had something like lithium 1s2, 2s1, the highest energy electrons, the outermost electrons, are the valence electrons. And these lower ones are known as core electrons. Only valence electrons are involved in bonding because they are furthest away from the nucleus. They're not held as tightly. And if you think about it, they are the furthest thing out there. So when two things come together, those are the first sort of electrons involved in contact with each other. Now, you could write the electron configuration for valence electrons, but nobody wants to do that. Again, a reminder that the number of valence electrons equals the group number on the periodic table. So everybody in group 1 has one valence electron, everybody in group 2 has 2, 3, 4, 5, 6, 7, 8, as you go all the way across. Bless you. The good news is in bonding, we don't do anything with transition metals, but it's also the group numbers for the transition metals. It is just a regular 1 through 18 numbering that you use for those kind of guys in the transition metal region. Now we use the symbol and basically one dot to represent each of those for a Lewis dot symbol. So we basically just use the symbol and we use basically one dot to represent each of the valence electrons. Kind of no real big rule other than maybe no more than 2 per side is usually the rule. And there's 4 sides to a symbol. That means how many electrons? Yeah. And 8 valence electrons on the periodic table is which one, people? Group number 8 is the noble gases. So as we'll talk about, as we maybe talked about a little bit before, the whole purpose of bonding, both ionic bonding and covalent bonding, is for everybody to achieve the same electron configuration as the noble gases because they're really, really stable. So 8's a really important number in bonding, and everybody's trying to become like the noble gases in terms of their electrons. We might have talked about it previously as well. They actually don't become, for example, the noble gas elements because the protons don't change. But in terms of their electrons, they end up the same as the noble gases. Here is some Lewis dot symbols or electron dot symbols I made one day. I was bored. I should really get a hobby, but that's 1 there, 2, 3, 4. I made this years ago when we didn't even have really good technology either. It was a long time ago. I cut and pasted all together. 6, 7, and 8, while I was watching my TV that was on the ground, with my CRT tube in it. Now, one exception, though, when we look at the valence electrons is group number 8, and that's helium. Helium is a member of group number 8, but helium only has 2 total electrons. So it can't obviously have 8 valence electrons. It only has 2. So helium actually only has 2 valence electrons because it has 2 total electrons. Everybody else in group 8 will have 8 valence electrons, and they will basically be filled. And that is over here is the goal of everybody in terms of bonding is to end up like those guys over there in group 8 in terms of their electrons. All right, so as we talked about, we can use these dot symbols to help us understand bonding, both ionic bonding, which again, as we talked about a number of times at this point, metal, nonmetal, and covalent bonding, which is 2 nonmetals together. The general rule is, if you think about the sort of periodic trends that was at the end of the previous chapter, basically as you go up and to the right on the periodic table, where we find our nonmetals, they all have properties of pretty much they like to hang on to their electrons. They like to take other people's electrons. So nonmetals, because of those periodic trends, really have the deal of I'm keeping my electrons and I'm actually looking to get some of your electrons. And that is different than what we see on the other side of the periodic table where we have our metals. They have all these trends of I'm not really interested in gaining electrons, and I'm not really all that interested in keep in mind. You could have them if you like. They're interested in just kind of giving away their electrons. You don't have to really convince them that hard for them to give up their electrons. And that is why we see cations form with metals because of those properties of it's okay, you can take my electrons. And why we see anions or negatively charged things occur with nonmetals because they have all those properties of I'm keeping my electrons, I'm going to take yours. So they tend to gain electrons when we go through it. Now, let's talk about how we make an ionic bond. And it is between a metal and nonmetal. We know lithium fluoride is LiF from our conversation earlier in this chapter. That is a metal. That is a nonmetal. That is a automatic ionic compound that we are going to make. So let's see how it comes together in terms of the bonding. So the first thing is lithium, and I go to the periodic table and I find lithium. He's hanging out there in group 1, which means he has how many valence electrons? 1. So we're going to draw a little lithium there with a dot. We're going to lay up his electron configuration because we learned all this crazy stuff. Why not? All right, 1s2, 2s1 is his electron configuration. By the way, the dot that we see in the structure there is his valence electron, and that is this electron right here. That is its valence electron right there is what we see. Fluorine is group number 7 there on the periodic table. That means how many valence electrons does it have? It has 7. So we're going to give fluorine 7 dots. And we'll do the electron configuration for it as well. 1s2, 2s2, a little 2p5 action. Remember that these first numbers are the energy levels. So those are 2s, which is the highest numbers in energy. And on these guys here, this where our 7 valence electrons are. 5 there and 2 there is the 7 valence electrons in fluorine. So now when these two guys get together, are near each other, the lithium is like, oh, go ahead, take my electron. I don't care. And the fluorine goes, cool, I was going to do that anyways, but thanks for letting me have it. Actual conversation, you probably have that right there. So what's going to happen is because of those periodic trends, we are going to get the transfer of electron that's going to happen in this case because it's going to have those trends and make the ionic compound. So lithium's going to shuttle its electron over to fluorine. The result of that is lithium has just given up an electron, which means it now has more protons than electrons, and now going to end up with a positive charge. That is how it becomes positively charged at this point. Fluorine goes, cool, thank you. I'm just going to pop that electron in where I have a spot for it, which happens to be right about there. And now fluorine has now gained an extra electron from lithium. And because when you gain an extra electron, you're now going to become negatively charged in this case. And lo and behold, we just made an ionic compound. There is absolutely no sharing of electrons here. What is holding these two things together is the opposite attraction of the charges. That is also why when you draw these Lewis sort of symbols for ionic bonding, you typically need to put the charges in to indicate that there's no sharing of electrons. And usually at least one of them, you put like a little bracket around it like I did with the fluorine, just to indicate that nobody's sharing electrons here, that they are separate from each other. First off, any questions on that? Now, what does this do for each of these sort of elements when this process takes place? Well, let me try not to erase everything. There we go. What's going to happen in this case is lithium on the right-hand side has given away its one valence electron, which now means if we write the electron configuration for lithium with a +1 charge, it is 1s2. That is how many total electrons? Number on top is 2. Yeah, this is how many electrons you got going on, right? And on the periodic table, who's number 2? It is helium. So by lithium giving away its electron, it was able to back up one space on the periodic table, and it now ends up in the same electron configuration as helium, which is really good because helium is a noble gas. So now it's going to make him very stable at this point. Now, fluorine's all good because its electron configuration here, when we look at the p subshell, by the way, p subshells could hold how many electrons? 6. Right now, that p subshell has how many electrons in it? 5. It's got room for one more, which is good because lithium just gave them an electron, right? It's going to put that electron that lithium gave them right into that spot. And now fluorine with his -1 charge will be 1s2, 2s2, 2p6. If you count up those top numbers, 6 plus 2 plus 2 is 10. Yeah. And who on the periodic table is number 10? Neon. Neon is also a noble gas. So that is the whole basis, right, of bonding. They just achieved what they wanted to do. Fluorine, by picking up that electron, goes forward on the periodic table to the noble gas that comes after it, making it really stable. They've all achieved noble gas configuration, which is as stable as you could get, and that's going to allow that bond to be a pretty stable bond that's going to form in this case. Any questions on that there? Yeah. Okay. Yeah, it's pretty much what we were just talking about. That yeah. So it's what we were talking about on the left-hand side. Groups 1 and 2 will form positive ions, and non-metals will form negative ions. Basically, yeah. Other questions? All right. Let's take a look at what we're talking about here. This is again an ionic bond. Once again, no sharing of electron. Both the metal and the non-metal are able to achieve that really stable noble gas configuration by losing and gaining electrons. And again, that is always what happens in an ionic compound. The metal will lose enough electrons, its valence electrons, to back up on the periodic table to the noble gas that comes before it. The non-metal will gain enough electrons from the metal to go forward on the periodic table to the noble gas that comes after it along the way. And once again, electrostatic attraction, positive, negative, holds that together. Absolutely, once again, no sharing of electrons. Now let's take a look at calcium oxide, also a metal and a non-metal, right? So once again, when we get that combination, we automatically know we're going to have an ionic bond. We're going to have some ions, some cations, and anions in this case. So let's start it here. Calcium is group number 2, so how many valence electrons should it have? 2. That's a couple of dots. I'll do a little electron configuration here. I'm going to do the shorthand, a little argon, 4s2. Yeah. By the way, that right there are the 2 valence electrons that you see as dots, that 4s2. And again, remember the argon is the entire configuration for argon, 1s2, 2s2, 2p6, 3s2, 3p6. That's argon's configuration. And then you could add 4s2 at the end, would be obviously calcium's completed, all written out. All right, oxide is oxygen. Yeah, I'm sorry. I'm good with argon. I'm good with argon as long as I say don't do it. Unless I say don't do it, but you could write it if it's like that, it's fine. Shorthand, yeah. Oxide is oxygen, and oxygen is group number 6 on the periodic table, which means it should have how many valence electrons? That's a good answer. 2, 4, and 6. A little electron configuration here for oxygen, a little 1s2, 2s2, 2p4 in this case. Again, we have the combination of metal and non-metal where the metal is going to go take my electrons, the non-metal is going to go thank you very much, I will. And we are going to again get the transfer of electrons that are going to come. Not just one electron, and that is because what would happen if you look at where calcium is on the periodic table and it only gave away one electron? It would move only one spot back, right? And it would move one spot back to potassium. Doesn't have the same ring as a noble gas, right? So it's going to want to give away not just one of its valence electrons, it's going to want to give away both of its valence electrons in this case. And when it does so, calcium got rid of not just one, but 2 electrons, which is then going to turn it into a positive 2 charge. Oxygen is good with that because once again, when we look at this P subshell, it only has 4 electrons in it, which means it's got room for good enough 2 more that's coming in, right? So it's got room for 2 more coming in. It will pick up those 2 electrons. And because it picked up 2 electrons, it will now have a minus 2 charge. And once again, there is no sharing of electrons. It is the positive charge and the negative charge here that is holding that unit together. First off, any questions on the drawing there? That also means that if we look at what happens in each of these cases, calcium laid up its 2 electrons, these 4s electrons. That leaves it with really 18 electrons, which is argon's configuration. Also a noble gas. So that's a check box for it becoming like a noble gas. Oxygen put those 2 electrons right there in the p orbital, which gave oxygen 1s2, 2s2, 2p6. Adding up the top numbers, 6, 2, and 2 again is 10. And that gets oxygen now to neon's configuration. That's a check mark for him as well because now both of these guys, by again gaining and losing electrons, are able to achieve that noble gas configuration. They're super stable at this point. That bond's going to be all good to go. Yes, it's going to hold together. No issues going to happen. Yeah. Any questions on that? Again, this is really the basis of all bonding, especially ionic bonding, for example, is to get to that noble gas configuration. Again, if you look at the periodic table, calcium achieves it by giving away 2 electrons, so it backs up to 18. Oxygen gains 2 electrons, goes forward to neon's configuration to get to that stable state. Now, what happens if we kind of combo those 2 guys together? What happens if I took a calcium that has our 2 valence electrons, starting with our argon 4s2 configuration, again, these 2 electrons, and I put it together with our friend fluorine that we saw in the first example, which has 2 P5. Once again, calcium being a metal, fluorine being a non-metal, we are going to get a transfer of electrons, right? So what's going to happen is my calcium is going to go take my electron, please. So it's going to send its electron over to fluorine. Now, can that fluorine, once it accepts that electron, take any more? No, it's kind of filled. Eight's like the max there, right? So you don't want to go over eight because that kind of overshoots the noble gases. That's again a problem for calcium because calcium in this case can only get rid of one electron, which once again takes him to potassium and not the noble gas that it wants to be. So that's not going to create anything that's going to be very, very stable. So how do we get around that? Well, in this case, calcium needs to go find himself another fluorine because that other fluorine has room for its second electron. It's going to send its second electron over to the second fluorine. And now, by giving away an electron to each of those fluorines, calcium is now able to give away both of the electrons that it wants to do. Each of those fluorines gained one electron. So fluorine number one gained only one electron. And because it only gained one electron, it ends up with a -1 charge, which is pretty good because fluorine is group number 7. It should have what type of charge? Only a -1 charge, right? So that's good. The second fluorine there, I'll just put it right about there, also gained only one electron. And it will gain a -1 charge in this particular case. So let's see what happened to all three of these guys. Well, our calcium was able to give away both of its valence electrons, one to each fluorine. That means my calcium here did hit the argon configuration by doing so. Now, each of the fluorines had how many room in its p orbital? It had room for one electron, right? So each of these fluorines ended up with 1s2, 2s2, 2p6, which is 10 electrons, or it ended up as neon's configuration. That's good for him. That's good for him. And this one did the exact same thing, picked up one electron, 1s2, 2s2, 2p6, or that is neon's configuration. So by calcium spreading out its electrons, one to each fluorine, all three of these things ended up in noble gas configuration, which is stable for all of them. Now, how does this tie together to perhaps something we just talked about? If we were just doing nomenclature and I told you I had a calcium with a +2 and a fluorine with a -1 and I put them together, they need to equal what charge? 0, right? Which you would then tell me I need how many more fluorines? One more to give me the proper formula of CaF2. This is the reason why it needs to equal 0 in the simplest way possible. Because when you put your positive ion together with your negative ion in the simplest way possible to get to 0, you're allowing everybody in that compound to basically reach noble gas configuration and get to that really stable state. So that is why when we take those ions and put them together and we say DC equals 0, it's really for the bonding reason here. That's going to allow everybody within those bonds to achieve that noble gas configuration. Obviously, if you put it together without reaching 0 and you just put it together like this, now you can see you're going to end up with something like this, which is going to make that calcium here only get the potassium, right? He's not going to be able to get all the way over there because he'll still have a +1 charge, and that is why it does need to equal 0. So the reason why when we talk about in naming that you have to put those ions together to equal 0, it actually has to do with the bonding aspect of it, that is what allows everybody to achieve that really stable configuration and that stable presence to make a bond. Any questions on that? Yeah. That is it. It might sound really difficult bonding, but if you want to cut it down to really what the point is, that's the point of it. Any bonding you want to talk about is for everybody to get to the same electron configuration as the noble gases just to be stable. Yeah. Are you talking about why I crossed this out? Yeah, the reason I crossed this out is if you were, for example, were just doing nomenclature and you said, I think this is the formula for the ionic compound. What is actually happening when you do that is that plus charge actually comes from the calcium, which means the calcium like a +1 charge kind of left over, if you will. And if it did, that would mean that it was only able to get rid of one of its electrons. It still has that one electron, and it would not be at noble gas configuration. It needs the extra fluorine there to be able to get rid of that extra valence electron and get it down to a +2 charge and back to noble gas configuration. And that's really, again, the reason why we talk about it needs to equal 0 when you put them together is, again, when you do that in the simplest way possible, everybody in that compound now is going to be in a stable noble gas configuration. Other questions? All right. That's ionic bonding. Fun. Let's talk about more fun. Covalent bonding. It's like ionic bonding. Maybe a few more dots. I don't know. Or maybe a few more lines. Maybe that's even better. There's maybe a few more lines. Clearly, my dots and lines are way off, so I'm just gonna kind of scratch it out and redraw it so we could actually, I don't know where my dots and electrons were flying to. All right, so Gilbert Lewis basically suggested covalent bonding as the idea of sharing electrons, and obviously that's why we call them Lewis structures after this guy. And when we get to covalent bonding, so there's no misunderstanding, this is very different than ionic bonding. So first off, with covalent bonding, there is no metal to be found. This is all about two nonmetals. Yeah. The other major difference is, unlike ionic bonding, where there is no sharing of electrons, this is all about sharing of electrons. So covalent bonding is all about sharing of electrons. Now, as we will talk about, the sharing could be equal sharing. It may be unequal sharing, but there is some aspect of sharing that's going to happen in a covalent bond. The reason we get sharing in a covalent bond is because we have two nonmetals together. And if you look on the periodic table, all the nonmetals are hanging out in the same location, which means when you talk about their periodic trends, both nonmetals have pretty similar periodic trends, which mean they both want to keep their electrons. Neither one of them want to give it up. They both want more electrons and take other people's electrons. So what happens when you get two nonmetals together is neither one wants to give away their electrons, but they both want to pick up the other guy's electrons. So the best that could happen is they decide, we're just going to share. How about we just share and we'll all be happy and all that good stuff. So because neither one of them is going to want to give away their electrons like the metal did in the ionic compound, where it's like, just take them, they're like, I want to hang on to them. So the best that they could compromise on is sharing. And in some cases, even though they say they want to share, one doesn't really want to share all that much, so it kind of pulls the electrons a little closer to them versus the other. Some are like, cool, we'll just equally share, we're good, just keep it nice and equal between us. But some are like, yeah, I'll share, but I kind of want to hog the electrons myself, but I'm still going to share with you. So what happens, for example, if we take hydrogen, by the way, which only has one electron total, so it can only have one valence electron, and we put it together, for example, with another hydrogen, they both definitely want to hang on to their electrons because remember, hydrogen's still a nonmetal, even though it's hanging out on the left-hand side of the periodic table. So what's going to happen in this case is these electrons here are going to end up being shared between the two hydrogens. So what happens is these two electrons get shared between the two hydrogens. So the electrons in the middle count for the hydrogen on the left, and those electrons in the middle count for the hydrogen on the right, which means if those electrons count for both of them, the hydrogen on the left ends up with how many electrons? And since it also counts for the guy to the right, the hydrogen on the right ends up with, and dare I ask the question, who on the periodic table is 2 electrons? Helium, yeah? So by sharing electrons here in the covalent bond, each of those hydrogens are able to achieve that noble gas configuration of helium. dot note, super important on bonding is if you look at the location of hydrogen on the periodic table and you look at the location of helium on the periodic table, hydrogen only needs to get to helium to get to a nice stable configuration. So hydrogen should never, ever, 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 never have more than 2 electrons. I say that because I've seen many tests where hydrogen has got like 32 electrons. And just for good measure, 42 bonds on it as well. I'm like, I'm not sure how you put all that around hydrogen or anything like that. It should only have 2 because it only needs to get to helium to be stable. So if you ever find yourself in future endeavors putting lots of dots around hydrogens and lots of lines, you probably should also put a big X over it because it's probably going to be wrong. Yeah, so just keep that in mind. That's a really good thing to remember. I don't know what it is with hydrogen. People just like, I think it looks better with a lot more things on it. All right, so you can represent this bonding. This is sharing of electrons, just like I did. You can use dots to represent that. Most of the time, people will use lines to represent the bonding that's happening. So you could also represent this bond by putting a line between the 2 hydrogens, and that would represent the 2 electrons that are being shared. So if you see one line between 2 elements, that represents 2 electrons that are being shared. That is also what is known as a single covalent bond. Excuse me. If you see 2 lines between 2 elements, that means that they're actually sharing 4 electrons, and this is what is referred to as a double bond. And lastly, if you see 3 lines between 2 elements, that is sharing a grand total of 6 electrons. Each line represents 2 electrons. That is what is known as a triple bond in this case. If you have 4 bonds, you drew too many. Yeah, so stop at 3. Yeah, so 3 is as much as you can get. Because by the time you get to the 3rd bond, that person on each side is going to definitely reach noble gas configuration. They don't need usually any more of that. At least not for our purposes on this class. They definitely don't. All right, any questions on that there? All right, so in a covalent bond, as I was mentioning before, what really holds that together is, if you think about it, electrons are negatively charged, and each of the atoms have a positively charged nucleus. So as those electrons kind of come between them, the electrons are kind of attracted to the nucleus of one and then also attracted to the nucleus of the other. And that's sort of what kind of keeps those electrons between the 2 atoms, is the mutual attraction to the positive nucleus, since the electrons are negative. So if we look at fluorine, fluorine is group number 7 on the periodic table, right? Which means it has 7 valence electrons. If we have 2 fluorines, it also will have 7 valence electrons. Since they are both fluorine, they're definitely not going to give away their electrons. They're going to share. So we're going to get some sharing of electrons going on in this case. And in this particular case, what's going to end up happening is each of the fluorines will share a pair of electrons between them. And once again, you can draw it with all dots if you like. And those 2 electrons on the left are in the middle, count for the fluorine on the left. And the 2 electrons in the middle will count for the fluorine on the right. And now, because they are sharing each of those electrons in the middle, fluorine on the left ends up with how many total electrons? It ends up with 8 electrons, right? 2, 4, 6, 8, including the ones that are being shared. The fluorine on the right ends up with 8. What things are on the periodic table on number 8? Those are the noble gases, right? Group number 8, right, has 8 valence electrons. So group number 8 has 8 valence electrons. So in this case, each fluorine, by sharing the electrons in the middle, have now successfully got all the way over here to group number 8, because those guys have 8 valence electrons, just like they do now in this bond. And now they have a nice stable bond. They each have reached basically that noble gas configuration. Once again, you can represent this with a line to show the bonding and not dots. So you could do just a line between the 2 fluorines. and you'll end up with something that looks like that. So they're both, acceptable drawings along the way. Now, when we look at something like this, there are a couple of different types of electrons involved in this. All of these electrons here on the outside are not involved in any type of bonding. I know that because there's no other element on the other side of the dots, right? So there's nothing hanging out on the other side of those dots. So there is no bonding happening there. So those electrons have a very special name because they are not involved in bonding. They are called non-bonding electrons. Very creative there. Or if you're really old like me, they are called lone pairs. Yeah. So if somebody says lone pairs like myself, it means the same as non-bonding electrons. And all of these guys over here that are non-involved in bonding, also non-bonding electrons. Now we do have a pair of electrons that is involved in bonding, and that is these electrons right here. And if you had to take a guess at what those are called bonding electrons. Also super creative there. So those are bonding electrons. So when somebody says bonding electrons, they should be part of a bond between two elements. If they are non-bonding electrons, they would basically be dots, and they're not really involved in any type of bonding with another element. Any questions on that there? Okay. All right. Now, a Lewis structure is a representation of covalent bonding, where again we kind of use these dot symbols and lines to show it. A are only showing the valence electrons. Each of these elements still have those core electrons that are not involved in bonding. So when we look at like fluorine at the end there, it has 8 valence electrons. It still has all its core electrons, its lower energy electrons along the way as well. If we look at something like water, just to finish out on here, if we drew the Lewis structure for water, it would look something like this. Or if we drew it with all dots, it will look like this. Now, in this particular case, we see a couple important things. When we look at the hydrogen here, by sharing with the oxygen, hydrogen on the left there ended up with how many electrons? 2, which is good because I said never, never, never a lot of times, and it should never have more than 2 electrons, right? Hydrogen on the right, magically as well, still only 2 electrons, right? So it ends up with 2 electrons. Now the oxygen in the middle, which by the way, since it's group number 6, started with 6 valence electrons, by sharing with both of the oxygens, will now end up with how many electrons? It will end up with 8 electrons. So once again here, what we see is through sharing of electrons and covalent bonding, all the elements involved in the bonds have ended up in that noble gas configuration, going to make it really stable. How many non-bonding electrons are there on the oxygen? There are 4. How many bonding electrons are there? Yeah. How many non-bonding electrons are there on the hydrogen? 0. That is the right answer. There should never be probably. And how many bonding electrons are there on hydrogen? There's 2, right? And that is pretty much what hydrogen should always look like if you remember nothing else from today. So I don't see weird drawings later on. Hydrogen pretty much should always be on the outside and pretty much should only look like that. Or if you're going to use dots, it should only look like that, also still on the outside. Don't ever put any more than that. Hopefully I drilled that into your head today. All right, we were laid up there.